Okay, this is Weka week 4, answers to the homework questions. Talks about setting a random seed, affects which random sample from the data set will be chosen for training. So how do we change the seed? So we go to here and here. You can change the seed here. Number 2, at minute 4:17, we see that you got 10 different results for the accuracy of J48. Why are there different results? So you can see there are 10 different results here. And what he did is he just changed the seed, repeated the training. So each time he's going to get a different accuracy. The idea is that if we randomly select a sample and do training and testing, we'll get an accuracy. But if we used a different sample, we may get another accuracy, and so maybe the best idea is just to repeat it several different times and then take the average of all those accuracies and report that as the best estimate of the accuracy of the model. Okay, this is about the baseline accuracy, concept of baseline accuracy, which is what the 0R Weka classifier does. In the weather, for example, in the weather nominal data set, class is whether they play golf or not. And if you look at the data set, there are 14 elements, and 5 of those elements they do play golf, and 9 they don't. So if that's all you knew, then if somebody new comes along and you want to predict whether they're going to play golf or not, you would just say, well, since they in the past they didn't play 9 versus they did play 5, you would then predict that this new person wouldn't play because that's called the majority class of the golf data set. Regarding question number 3, which classifier behaves like the guessing we made here? We just said that's the 0R classifier. Okay, if you look around minute 6, you find the answer to this question. He shows that with a certain data set, many of the algorithms do worse than the base learner, do worse than 0R, and he just showed a bunch of them. So for example, this one, the lazy IBK, only gets 38%, but I think the baseline was something like 63%. So it does worse than the baseline, or worse than 0R. So that is the answer for number 5. Okay, the next question actually was a mistake, should go in this video. And it says he repeated the experiment 10 times. Standard deviation, if you look here, he repeated it 10 times. And we can calculate the mean of this. And that's a good way to estimate the accuracy of the algorithm. But the other thing you can do is you can say, well, how much variation is there in these numbers? Let's suppose if I look at these numbers, the mean is about 94. So suppose the mean was about 94. The mean is, doesn't tell me, here, the mean is 94.9, so almost 95. Okay, so let's say the mean was 95. Now we can see that sometimes it's obviously above 95, sometimes it's below 95. Here it's a little above 95, here it's more above. So there's some variation in the data around 95. But there, maybe 1 or 2 percentage points above, not even that, and 1 or 2 percentage points below, not even that. But you could also have a case where instead of these numbers, maybe you got numbers like 85, let's say 90, sometimes you got 90s in here, and sometimes you got 100, and sometimes you got 91, and other times you got 99. So the mean might still work out to about 95, but the variation is much greater. So that kind of points to kind of a less accuracy or less confidence in our predictions than in this case where it's very close to 95. Maybe you don't necessarily agree with that statement, but anyway, there could be more variation around 95. And that's what this measures. The sigma is the variation around 95. So we're also interested in the variation around 95. So again, this question 6 actually it refers to this video here. And what was the value of the variance of the estimate? So that was this number, whatever it was here, 0.018. Okay, let's talk about cross-validation next. You can see 2 pi's. What are they? Let's see that. So here we see 2 pi's, and this is explaining the idea of cross-validation. So you take the whole circle represents the entire data set, and you split it up into usually 10. We call them folds, 10 folds. And then you take one of them out, and you do the training on the rest of them and test on the blue one. And then you get an estimate of the accuracy. And then you repeat it again, but this time you take a different slice out for testing, train on the other ones. And you do that for all 10 slices. You hold out that one of them for testing. And then you can average all of the estimates of the accuracy to get the sort of most realistic estimate of the accuracy. Okay, let's see. Okay, so there's 2 concepts here. One is to measure the accuracy, and the other is to have an algorithm, or a model to use in the future. So if we want to make our model, we may as well use all of the data to make our model. We're going to use it for future data that we don't have right now. So we may as well make our model with all of the data, but we saw that we don't, that's not exactly how we measure the accuracy of our algorithm. So we just said how we measure the accuracy is, for example, tenfold cross-validation. So that we just explained that. But to build the algorithm for future use, as I said, we may as well use the entire data set. And that's what he means by for deploying the model, for using it in the future. We use the whole data set. So that's what he means here. Okay, in this video, this is the next video. Here we have the holdout method, and he's holding out 10%, and then as we said, we could just set a different seed, and we'll get different results. So he gets 10 different results here, and he can average them, and the average turns out to 74.8, and the standard deviation turns out to 4.6. Okay, so what is meant by a fold? We just saw that the folds are those pie slices. And then one more thing here we should mention, a little bit surprising. So here's what we did. Here's what we got when we did the holdout. So we got the average was for this particular data and this particular model is 74.8, and the standard deviation was 4.6. So again, what the standard deviation means is that sometimes we might get something like 74 right in the middle, but we could get like 74 plus 4.6, which would be like 78 or 79. We might get something like much smaller, smaller than 74, like 74 minus 4, which would be around 70. So we're saying we could get things like 70 and 79. So there's quite a bit of variation there. On the other hand, when we do the cross-fold validation, if we could actually look at it, I don't think we can see what the results are like this. But if we do it, here we'll get maybe basically the same as we got here, but the standard deviation is much smaller, and that's a good thing. We want the standard deviation to be small, and it seems to be a lot smaller. And so what's the possible reason for that? Well, remember, in cross-validation, we are testing on every single instance, because first we take out one slice, then we take out another slice, then we take out another slice, and we're going to get through all of the slices, so we're going to get through the entire pie. But here, it's not quite guaranteed that we're going to do that, because we're just randomly selecting 10% for testing then randomly selecting another 10% protecting. It's not clear that we're going to get, for example, we're never going to repeat like what happened in this test. There might be some of the data points might appear in here, and some of those might appear in here, and so on. Whereas that will never happen here, because we're literally splitting the data set into 10 different ones and only choosing a slice for testing only once. So that, I guess, is the reason why this turns out to have a higher variance or standard deviation than this. So cross-validation, although it seems like it's the same thing as holdout, when you hold out 10%, but it's really not, because here we're guaranteed to get to be testing on every single value in the data set, whereas here we're not really guaranteed of that. And somehow that leads to a smaller variation here, smaller standard deviation. Okay, so this is the next video. And at the minute 220, he says each branch assigns the most frequent class that comes down that branch. So, for example, here we have petal width. So actually, I think he's talking about 1R, but the same applies for J48. So here we have petal width. If it's greater than 0.6, then the next decision is if it's greater than 1.7. And then it predicts Irish Virginica, and that's because examples are the flowers that have petal width which is greater than 1.6 and greater than 1.7, greater than 0.6 and greater than 1.7. From that set, most of them will be Irish Virginica, and so it classifies them in general as Irish Virginica. Okay, the next question refers to the weather data set. So let's have the weather data set here. If it's sunny, how many yeses are there and how many no's? Here's sunny, 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 and sunny. So these two are both no. This one is no, this one is yes, and this one is yes. We had 3 no's and 2 yeses. So we could make a rule that if it's sunny, that the answer to this question number 12 is if it's sunny, then we would say no, because that's the most frequent class when it's sunny. So if we made that rule, this is question number 13, and we use the entire data set to test, then we would make, I think we just said 2 errors. Okay, at around minute 5, he says there's a tie. So he's saying that a variable will produce a pure node. Outlook and humidity both will result in the same purity. Okay, when you use cross-validation with tenfold on the weather nominal, what does the rule 1R generate? Why doesn't it generate a rule based on windy? So it uses outlook. So we could ask, why doesn't it use a rule based on windy, which was another of the variables, another of the attribute. But outlook produces a better prediction, a better accuracy than does windy. Okay, if we use percentage split here, we still split on outlook, but the accuracy is 40%. Okay, who wrote the 1R algorithm? I think it would be under, let's see. Sorry, there it is. This person wrote it, and it was written in 1993. Okay, so he uses this is for overfitting, the video on overfitting. He uses the phrase, if your model overfits the training data, it doesn't generalize well to independent test data. Explain that in simpler language. Well, one way to explain it is to say that the model will fit the noise, and then when we're trying to predict with independent test data, the noise will be different, and so the model won't work very well. That's one way to explain it. Okay, around second 40, he talks about the user classifier. I believe we selected more than 10 instances using the selection tool. Okay, so there's, besides the weather nominal file that we use most of the time, there's also the weather numeric file. If we look at that, if we look at temperature, it has actual numeric values. Humidity also has numeric values. Windy has nominal values still, and play is nominal. So we get more numeric values when we use the weather numeric. you can open up a file, an R file, using something like Notepad++. And I have Notepad++ installed. It comes up here, so I can open it with this. And I can see that the first record, what's the temperature? We can see, I think it's 85. Temperature is the second variable. So here. The next question is, how many different values of temperature are there? There's 85, 80, that's 2, 3, 4, 5, 6, 7, 8, that was repeated, 9, 10. Maybe there are 10 different values. So if 1R was testing the temperature, so this is question 22, if 1R was testing the temperature attribute, it would have to have 10 different branches. So that would turn into a very complex model, and we talked about overfitting. When you increase the complexity of the model, you tend to get higher accuracy, but you also tend to get worse generalization, generalizing to independent test data. So here, if we look at temperature equals 64, so when temperature equals 64, first of all, what will we predict? Well, there's only one case where temperature equals 64, so we would predict yes, and the error would be 0, because there's only one case and we predicted it correctly. The same would be true for 65, because there's only one case of that. 68, only one case. 69, only one case. So they would all have 0 errors. And that's part of the reason why we would say that the model will be more accurate on the training set, but probably not on the testing set. Okay, so we just talked about the answer to 24, the first part. What about the minimum bucket size? What does that do when we increase the minimum bucket size? So the minimum bucket size, as you increase it, will tend to reduce the overfitting. So if you make the minimum bucket size very small, then, for example, if you set it to 1, generally that, for example, he does an example here at minute 608, where it branches at every value of this particular variable that it's chosen. It chose some variable called PED, and basically you can see that it's branching at every value of that variable. So that would make it very accurate for the training set, but not accurate for the test set. We can reduce that problem by increasing the minimum bucket size. And the default setting for minimum bucket size is equal to 6, I believe. So here, I think you can see that J48 is just a more elaborate form of 1R. It does the same thing that 1R does, but it does it for each. It allows us to create nodes below the root node, nodes below those as well. Okay, for using probabilities, I think I'll make a separate video